Hi, my name is Stoica. I am a faculty at UC Berkeley, and I am also the director of the Sky Computing Lab. I am also the co-founder and executive chairman of both Anyscale and Databricks. During my career, I was involved in several open source projects, including Apache Mesos, Apache Spark, Alusho, and Ray. As these projects became popular, they were backed by companies to ensure their long-term viability and growth. In this talk, I will focus on the last and the most recent of these projects, Ray. This talk is organized in 4 sections. I will start with strengths and challenges in AI that have motivated our work on Ray. I will then provide a short overview of Ray, and I will conclude with several Ray use cases. So let me start with the trends. It is more and more clear, and not only because of the huge impact ChatGPT had over the last couple of months, that AI will disrupt every industry: finance, healthcare, transportation, manufacturing, and more. At the same time, the compute demands of AI applications continue to grow much faster than the capabilities of a single node or a single processor. Here is a plot from the last year showing that over the past 12 years, the compute demands requiring to train state-of-the-art machine learning models have doubled every 5.7 months. This is equivalent to the compute demands growing about 10 times every 18 months. So why is this? Well, one reason is that large models have been shown to achieve much better accuracy. This is a plot from the GPT-3 seminal paper published in 2020, which shows that the accuracy of a model increases significantly with its size. And this is for a variety of training and fine-tuning tasks, including zero-shot, one-shot, and a few shots learning. Another reason is the emergence of the foundation models that have been shown to be effective in learning multiple tasks, as well as improving individual tasks. This is a great animation illustrating these points that we borrowed from the last year's Google's post on Palm, their pathway language model. In contrast, according to the well-known Moore's law, which powered the compute industry until the beginning of this century, the performance of a single core only doubled every 18 months. Worse yet, since then, the performance growth started to slow down. Today, per core performance improves just a few percent every 18 months. To put things into perspective, here I am overlaying the Moore's law performance increase, as well as the real per core performance increase on the previous plot. The gap between the compute demands of training the state-of-the-art models and the performance of a single core is huge and is growing rapidly. In fact, note that even if the Moore's law weren't ending, it would have been of little help to bridge the gap. But what about specialized hardware, you may ask? After all, over the past decade, we have seen a plethora of new hardware accelerators being released to better support these AI workloads. Well, it turns out that while specialized hardware accelerators certainly helps, they are not enough. Here I am overlaying the performance for both NVIDIA GPUs and Google TPUs on the same plot. Note that despite the fact that the Moore's law has slowed down, these processors are still able to provide about a 2 times performance improvement every 18 months. They do so not necessarily by increasing only the number of transistors, but also by aggressively specializing their hardware architecture for deep learning workloads. However, despite the impressive increase in performance of these specialized processors, they are still falling way short of satisfying the compute demands of training state-of-the-art machine learning models. The gap still continues to grow and continues to grow exponentially. Now, over the past several months, you might have read some headlines that the age of huge AI models is ending. Indeed, even Sam Altman, the OpenAI co-founder and CEO, was quoted saying this in April this year. However, in a more recent interview, Sam Altman clarified his position. In short, OpenAI's internal data suggests that the scaling law still holds. That is, model performance continues to improve with the model size. However, what is different is that due to the huge cost and GPU shortage, it is no longer feasible to increase the model size by 10 times every year. Instead, models are expected to just double in size or maybe triple every year. But even if the machine learning models were to stop increasing in size, it will take decades for specialized processors to catch up. For example, consider a recently released PAL model from Google. This is not the largest model, but it still requires over 6,000 of the later generation TPUs to train. Assuming the performance of these processors continue to double every 18 months, which is a big if, it will take almost 19 years to be able to train the same model in roughly the same time on a single processor. As such, there is no way to run these AI workloads, but to distribute them on many processors, on many machines. This is already true today, and we believe it will remain true for the foreseeable future. Next, let me talk about the challenges of building a machine learning applications or pipeline. So far, I only talk about training. But of course, a machine learning application or a pipeline is more complex. Most machine learning pipelines consist of 3 stages. First, the data preprocessing stage, where you ingest the data, featureize the data, or compute the documents embeddings. Then, you take this data and you train it. And finally, you take the trained models and you serve it. In addition, some machine learning pipelines might include high parameter tuning to tune the model, and batch prediction to evaluate the model before deploying it in production. Now imagine that we need to scale each of these stages. While we have distributed systems to scale each of these stages in isolation, we would need then to stitch all the systems together to build our end-to-end pipeline. Unfortunately, such solution is far from optimal. First, it is hard to develop because each system comes with its own API. Then it is hard to deploy and is hard to manage, and each system has its own semantics when it comes to fault tolerance and data consistency, and these semantics are hard to compose. And finally, the end-to-end pipeline can be slow as to move the data between the stages. We typically need to read the data, to write the data and read the data from persistent stores like blob stores, which is slow. We developed Ray to address these very challenges. Ray is a unified compute framework for distributed application that is general enough to scale all these machine learning workloads and more. But instead of using different systems to scale each stage of a machine learning pipeline, with Ray you can use different libraries running on top of Ray to scale each of these stages. So now there is no need to stitch together a bunch of disparate systems. Instead, Ray enables you to implement your entire machine learning application using a single system. Ray started as a class project at Berkeley in 2016. Its initial goal was to scale deep neural network training and reinforcement learning. In 2017, we released the first 2 libraries on top of Ray, RLLib for reinforcement learning and RayTune for high parameter tuning. In 2019, Anyscale was founded. Anyscale is a company behind Ray. In 2020, we released Ray version 1.0, and which includes a new libraries, RayServe, to serve machine learning models. Then in 2022, we released version 2.0, which includes AI runtime, or AI for short, we seamlessly integrate all the machine learning libraries on top of Ray. Ray has a very minimalistic yet flexible API. The core API has just 6 calls. I will not go over each of these APIs individually. Instead, I will illustrate the most important ones via a few simple examples. But first, why is Ray so general? To understand this, let's discuss the 4 key concepts in Ray that together we spell as fast. First, Ray takes the 2 compute abstraction provided by most procedural languages today, function and classes, and provides the ability to execute them transparently and remotely as tasks and actors. Second, Ray executes task and actors methods asynchronously. That is, when we spawn a task or an actor method, we immediately get back a reference to its return value. We call such reference a distributed future, or a future for short. Future enables a parallel execution of task and actors methods. Finally, Ray employs a shared in-memory object store to improve the performance and efficiency of passing large amounts of data between tasks and actors. Ray's core is written in C++, and it provides bindings for several languages. The most mature and popular binding is for Python. Here is a trivial example to illustrate how Ray works. Consider the following Python code, which consists of a function f, which takes 1 second. And then we invoke this function twice. And therefore, the entire program, it will take 2 seconds because the execution of each invocation takes 1 second. Now notice there is no dependence between the 2 functions. So in theory, we can execute this function in parallel. Ray allows you to do that. So let's see how it's doing that. Now, to execute f remotely and in parallel as a task, we need to decorate f of x declaration with ray.remote. Also, when we invoke the function, we need to add a suffix.remote to the function call. So let's see what happens now as we invoke the function the first time. Well, in this case, we spawn a task. And before the task is scheduled or even executed, we return a future. In this case, x sub id. Remember, the future is a reference to the task return value. Because this call is non-blocking and returns immediately, we can now call the second invocation, we can invoke the second time function f and assume this function f, again, is going to be run on a different node, a different worker, and is going to return again immediately a future. Finally, we call ray.get to obtain the results returned by both f of a and f of b. The important point to note here is that in this case, f of a and f of b are going to be executed in parallel because they are called basically at the same time and they are executed on different workers. Eventually, each of these functions will finish the executions and is going to return the results to the ray.get function, which will eventually display these results. Now, because f of a and f of b are executed in parallel, now it takes just 1 second instead of 2 to finish the entire program. Similarly, Ray allows a programmer to instantiate remotely a class as an actor. To do so, again, we decorate the class with ray.remote and use a .remote suffix when instantiating the class as an actor and invoking its methods. Finally, Ray also allows developers to specify the amount of resources to allocate when a task or actors are created. So far, we illustrated task, actors, and futures. The final key component of Ray is a shared in-memory store. To illustrate how this component is working, consider again a simple example. In this example, we consider a function g which takes as an argument the result returned by a function f. Assume that function f is going to be executed on node 2, and which is going to return, you are going to return yet again a future, which is going to be passed to g. And function g is going to be remotely executed as a task on node 3. Now, because g needs the results from f, it needs to wait for f to execute. When this result is available, call it x. X will be transferred to node 3, and G now can take X and start executing. To understand the advantage of the shared in-memory object store, assume this store did not exist. Now, in this case, the F result would have to be sent back to node 1 in order to be passed to node G and then sent to node 3 where G is going to get executed. So without a shared in-memory object store, instead of transferring X only once from between node 2 and node 3, we have to transfer it twice. Once between node 2 and node 1, and a second time between node 1 and node 3. As part of Ray 2.0, last year we also released the alpha versions of Ray Air, where Ray Air, or Air, stands for AI runtime. Air integrates seamlessly machine learning libraries for different workloads. Ray Air has integration with many popular third-party tools and systems. For example, Ray Data is from many external data storage systems like Databricks and Snowflake. Ray Train supports common machine learning libraries like PyTorch, TensorFlow, and more. Ray Tunes works with existing hyperparameter tuning systems like Optuna and HyperOpt, as well with experimental tracking systems like MLflow and rate and biases. And RayServe supports Flask, FastAPI, Gradio, and provides also monitoring and observability. Now, to illustrate the advantage of Ray Air, let me take another simple example. So let's say you have an end-to-end pipeline you want to scale with Ray, which consists of data preprocessing, training, hyperparameter tuning, and batch prediction. The takeaway of this example will be that Ray Air allows you to implement the entire pipeline using a single script with an intuitive API. So let's start. First, let's take a look at data preprocessing. Here we load a CSV file from some custom location, like a file storage. We then generate a training and validation dataset. And we also generate a test dataset by removing the column we want to predict. Finally, we create a preprocessor which will normalize a given column of the dataset, in this case, mean radius. Now, let's move to training. For model training, I'll use a transformer model available from Hugging Face. In this example, we are passing both the training and validation datasets, in addition with the preprocessor we defined earlier. By calling trainer fit, we'll process the training dataset with a given preprocessor and train our transformer model on the resulting dataset. The validation dataset will be used to generate validation statistics and avoid overfitting. We can also pass this trainer to a tuner object. We can specify the hyperparameter space to sample and the metric we want to optimize for, in this case, minimizing the loss rate. Notice here that both the trainer and the tuner can be distributed. By calling tuner.fit, here we can get a checkpoint with the best model. Next, we take the best trained model checkpoint from the tuner and pass it into the batch predictor module. There are two key points to notice in this example. First, you can implement your entire pipeline with a single script. Second, you can scale it from your laptop to a cluster with just a few line changes. Finally, RayServe lets you deploy the model and expose an endpoint for your application. Again, with a very simple API. Finally, a few use cases of Ray. Ray it's emerging as a compute framework for modern machine learning infrastructure. In one example, Shopify has used Ray to implement its next-generation machine learning platform. The generality of Ray enables them to support the entire machine learning lifecycle using a single system. In their own words, our bet on Ray to power our machine learning platform is proving instrumental in our ability to accelerate and scale our entire machine learning lifecycle. Maybe not surprising, Ray is emerging as a compute framework powering large language model workloads and applications, as shown in this diagram. There is the application in context learning and fine-tuning layers. In other use cases, Ray has been used by OpenAI to train its largest models, including ChatGPT, as well as by Cohere to train their large language models. And in the context of large language models, Ray is being used not only to train this model, but also to serve these models, as well as to scale other components of a large language model application, such as document embedding generation, as shown in this slide. To conclude, Ray is a distributed compute framework that dramatically simplifies building machine learning infrastructure and platforms, as well as scaling and productizing large language models applications. Thank you.